testing audio.
Okay. Hello, testing. Testing. See, 5. Testing 1, 2, 3.
Yeah.
Kareem. And thank you for the invitation to come visit today. Even though I've spent essentially my entire career in Pasadena at this point, it's gotten harder as I've gotten older to find time to make the arduous journey over here from the other side of the 210. So it's nice to have an opportunity to actually spend a day here and catch up with some of the people that I knew a long time ago and meet some of the new folks. Did you want to adjust the mic settings? How's that? Okay, good. So what I'd like to do today is give you an overview of the state of the field of dwarf galaxies, focusing on the satellite galaxies of the Milky Way. Last week, you guys had a colloquium from Xiaohui Fan focusing on the biggest and brightest galaxies in the universe. And today I'm going to go all the way to the other end of the spectrum, the tiniest, most pathetic galaxies that we've ever found. And my initial work on this area was done as a postdoc at Caltech here 20 years ago. Back then, just 1 or 2 Keck nights was all you needed to really clean up. And sadly, that's no longer the case. So let's start by defining the galaxies that we're going to be discussing. So these so-called ultra-faint dwarf galaxies are systems with luminosities less than 10 to the 5 solar luminosities, or in absolute magnitudes, they're fainter than -7.7. These objects are found using sky survey data. Basically, you look for stellar overdensities where the stars in the overdensity lie along a red giant branch or a blue horizontal branch, as you can see in this example from one of the first objects to be discovered by Beth Willman. And then, so this dwarf galaxy that's shown here is in Ursa Major. In comparison, this is the color magnitude diagram of the previously faintest known galaxy at this time in 2005, which you can see has an order of magnitude more stars in it than these ultra-faint systems. So I think it's fair to ask why such tiny galaxies might be of interest to anybody. Unlike in some areas of astronomy, nobody starts studying dwarf galaxies for the aesthetics. These objects shown here are 2 of the most recent discoveries. These are the ones where I could actually find a picture where you could see some stars in the center of the field. In most of them, that's not even the case. So most of the work on these systems has been motivated by a couple of key properties that they have. First of all, these dwarfs live in the smallest dark matter halos that formed any stars. And that makes them ideal objects for being able to constrain the properties of dark matter particles or test dark matter models. Now, there may be even lower mass dark matter halos than the halos these things live in. That would be very interesting. But if they don't have any stars in them, then they're a lot harder to detect and measure anything. And then the second reason that we study these things is that they give us particularly clean windows to study processes that happened in the early universe, such as nucleosynthesis, chemical evolution, that are very difficult to observe in situ. So we are able to detect galaxies from a few hundred million years after the Big Bang now directly. But unlike those objects observed with JWST, these ultra-faint dwarfs are not sitting all the way across the universe from us. They're just in our backyard. They formed their stars very early on, and then they've been passively evolving ever since. So to be a little more specific on the dark matter end of things, dwarf galaxies are responsible for many of the strongest constraints that we have on dark matter models. I've given a few examples on this slide. So for fuzzy dark matter, Dalal and Kravtsov placed a limit on the lower limit on the mass of a fuzzy dark matter particle that rules out most of the interesting parameter space from a physics perspective. Similarly, Ethan Nadler and collaborators placed a lower limit on warm dark matter, which is stronger than what you can determine from the cosmic microwave background or the Lyman alpha forest. Primordial black hole dark matter can be constrained by certain properties of dwarf galaxies. And Tim Brandt used this 10 years ago to close one of the few remaining mass windows in which primordial black holes could constitute the dark matter. And then most recently, Wendy Crumrine from USC used the dwarf galaxy population to place the best existing limits on interactions between dark matter and photons or neutrinos. Again, as in the case of warm dark matter, these limits from dwarf galaxies are stronger than what you can get from the microwave background and other methods. And so it's important to note that in some cases, these constraints are derived from considering the population of dwarf galaxies as a whole. And in that case, discovering new objects gives us a larger sample and helps us tighten those constraints. In other cases, these are just a result of the particularly extreme properties of one or a few objects. And so there too, discovering a larger sample of dwarfs gives us a higher probability of uncovering those types of extreme objects. Then in the chemical evolution space, these dwarf galaxies have very small stellar populations, and they have very weak gravitational potential wells. And that enables us to study nucleosynthesis in ways that are difficult in larger galaxies like the Milky Way. So probably the most spectacular example of this is the dwarf galaxy Reticulum 2, where Alex G showed about 10 years ago that the stars in this galaxy are enriched by about a factor of 100 in our process elements compared to every similar galaxy that we've studied. And so we were able to show that this is a result of a single event that occurred within the first 500 million years of star formation in this system that created a large quantity of our process material, which we suggested at the time was a neutron star merger a year before GW 170817. It is the timing of this event relative to the star formation is potentially in tension with that hypothesis. And so you might argue that a collapsed star is more likely, but in any case, this does provide insight into how these elements were synthesized in the very early universe. And then a more recent example is from Ani Chidi and collaborators last year, who identified an ultra metal poor star, one of the few most metal poor stars ever found in the outskirts of the dwarf galaxy Pictor 2. Like most of the stars in the Milky Way at this metallicity, the star is enhanced in carbon by about a factor of 1,000. And so what's thought to be responsible for this is it was enriched by a population 3 supernova explosion. If that supernova had a low energy, then it could have ejected all of the carbon it synthesized, whereas the heavier elements fall back into the compact object, and you end up with a carbon-rich composition. And this is the first time that this has been seen at such a low metallicity in a dwarf galaxy, where the potential well is so weak that you would, with a normal explosion energy, you would expect all of the heavy elements to escape. And so the detection of such a star in Pictor 2 supports this, this idea that this is the process responsible for this chemical signature. So here's a timeline of dwarf galaxy discoveries over the last 95 years. The first Milky Way satellite galaxies, other than the Magellanic Clouds, of course, were discovered in the late 1930s by Shapley using photographic data. And then the discoveries trickled in 1 or 2 every decade for the rest of the 20th century. And it wasn't until the advent of the Sloan Digital Sky Survey in the early 2000s that we actually started finding a significant new population. So Sloan very quickly doubled the number of Milky Way satellite galaxies. Then things plateaued for a bit until the Dark Energy Survey kicked in. We again very quickly doubled the population up to about 60 objects. And we've been perhaps turning over into another plateau here. with a small contribution from the Delve survey, also from the dark energy camera. And we are now expecting that the Rubin Observatory is going to contribute to yet a third doubling of the population in the coming years, bringing us up to a total of something like 150, 200 total Milky Way satellite galaxies. Now, it's important to keep in mind that what you discover from these sky surveys is not, strictly speaking, dwarf galaxies. You discover stellar overdensities that might be dwarf galaxies. And then we have to determine whether or not those systems are in fact dwarfs if we want to use them to learn about dark matter and other things. And so the community has settled on this definition of a dwarf galaxy proposed by Beth Willman and Jay Strader in 2012, where a galaxy is a gravitationally bound collection of stars whose properties cannot be explained by only relying on baryonic physics and Newtonian gravity. In essence, what this means is that galaxies live in dark matter halos. And other stellar systems, for example, clusters, do not form and reside in their own dark matter halos. A cluster may form in the dark matter halo of a more massive object, but there's currently no evidence that they form in their own halos. So then, observationally, the way that we try to make use of this definition is to measure a velocity dispersion that we can use to infer a dynamical mass. And then if the dynamical mass is larger than the stellar mass, we conclude that this object has a dark matter halo and therefore is a galaxy. In many cases, as I'll show you, we're running into systems where we can't actually measure a velocity dispersion. We just get an upper limit. And so another approach that people use is to measure a dispersion in the metallicities of the stars. We know empirically that globular clusters do not display a range in metallicities among their stars. And so the hypothesis is that, again, a dark matter halo is required in order for any of the supernova ejecta to be retained by the system and enrich it. And we can discuss whether energetically that is a sensible requirement to make, but that is what the field has been using. Now, so from the sky survey data, from just imaging, there are a very limited set of properties that you can measure for dwarf galaxies or any other stellar systems in the Milky Way halo. Some of the key parameters you can measure are luminosity, absolute magnitude, and a size. And so if you just plot all of the objects in the Milky Way halo in this parameter space, you get this plot here. So we have a set of compact, mostly pretty bright systems. These are the globular clusters. We have a set of much more extended systems, which are the dwarf galaxies. And then at fainter magnitudes and small sizes, we have a whole mess of other things where it's not necessarily obvious a priori whether these are the extension of the dwarf galaxy sequence to smaller sizes or an extension of the globular cluster population to fainter magnitudes. And so the only way we can actually determine the nature of these objects is by getting spectroscopy. Now, from spectroscopy of stars in these dwarf galaxies, we can measure their masses, we can measure their metallicities, and we can measure their chemical abundance patterns. There are two basic approaches that are used in this game. One is to do medium resolution spectroscopy of the calcium triplet lines at about 8,500 angstroms. This gives us a nice clean set of features that we can use to measure the velocity of the star. And then these lines are also metallicity sensitive for red giants. So we can measure metallicities from the same data. The other approach is to use higher resolution spectroscopy of the magnesium triplet at about 5,200 angstroms. This has the advantage that it can provide more precise velocity measurements, but the disadvantage that high resolution, of course, you get lower signal to noise, It's more difficult to measure metallicities from this very limited spectral range than it is from the calcium triplet. Some of the key results that have been obtained over the last 2 decades from this kind of spectroscopic follow-up of dwarf galaxies are we've shown that most of the dwarf population is very highly dark matter dominated. We find mass to light ratios for most of these systems of in the range of hundreds to thousands. So system with a stellar mass of 10 to the 3 solar masses may have a dark matter mass in its center of 10 to the 6 solar masses. Evan Kirby, 10 to 15 years ago, showed that the luminosity metallicity relationship of galaxies extends all the way from massive galaxies like the Milky Way down to on the order of 1,000 solar luminosities. It may flatten out at even fainter systems, but this relationship extends for many orders of magnitude below what was previously known for larger galaxies. And then, as I mentioned, we've detected things like this extreme R-process enrichment in reticulum-2. So the state of the art for what you can measure in these dwarf galaxies is this. So we can measure stellar velocities to about 1 kilometer per second. And keep in mind that when I'm talking about the state of the art, I'm referring to metal poor stars at faint magnitudes, mostly in the range of 19 to 22. Of course, for brighter stars, you can measure much better velocities, but that's harder in the dwarf galaxy regime. So with these 1 kilometer per second velocities, we can generally constrain velocity dispersions down to about 2 kilometers per second. We can measure metallicities from our calcium triplet lines with a typical precision of about 0.15 dex. And so that, again, enables us to measure metallicity dispersions on the order of 0.2 to 0.3 dex in most of these systems. And in the cases where we find stars that are bright enough for high resolution spectroscopy, then of course we can measure the chemical abundances of a large number of elements, 20 or even more in some cases. So one of the main goals of my work over the last 10 years in particular, but going back even farther than that, is to try to fully characterize the population of Milky Way satellites so that we know how many objects we have that we can use for dark matter studies, and we can learn as much as we can about their chemical abundances. So out of a total of 68 objects that are either confirmed dwarf galaxies or we have some reason to suspect are dwarfs, even though we haven't been able to formally confirm them yet, we've been able to measure a velocity and a velocity dispersion and a mean metallicity for about 80% of the sample now. So we're doing pretty well in that sense, but there are other ways in which we still have quite a ways to go in order to characterize the population. So less than half of the Milky Way satellites currently have high resolution spectroscopy of even one star from which we can measure chemical abundances. And only about 2/3 of them have a classification that we're very confident in based on the definition from Willman and Strader, where we measure either a velocity dispersion or a metallicity dispersion for the system. And so the main challenge that we face with studying these kinds of galaxies is that they just don't contain very many stars. So in the top set of plots here, I'm showing color magnitude diagrams for 3 dwarfs at a distance of about 30 kiloparsecs. So these are some of the closest dwarfs to us for a set of luminosities going from very faint on the left to somewhat brighter on the right. And so for the most luminous dwarf galaxy here, you can see a clear red giant branch quite easily. And then when you go down to this faintest system, Segway 1, it only contains a total of 7 red giants in the whole galaxy. And so if you want to have any stars to get spectra of, then you really need to get down onto the main sequence where the stars are much fainter. And then if you put these things out at the virial radius of the Milky Way, 250 kiloparsecs, then you can see that essentially none of the stars are bright enough for us to get useful spectra of now. So in a really one of the lowest luminosity galaxies here, the brightest member stars would be down at around 23rd magnitude. As you go to somewhat more luminous systems, they may just get a handful of stars that you could get a useful spectrum of with Keck, but it's really quite difficult with current instruments. And then the challenge that we are very soon going to be facing is that there are going to be a lot of candidate satellites that Rubin discovers that we're going to want to get follow-up for. So here's a picture of the sky distribution of the known satellites as of today. This is just a very simple toy model of what we might have in a few years from Rubin. And so the population is going to double, but if you take into account the candidates that are not confirmed, then the things that we're going to want to follow up, there's going to be even more of those. And so I've done a little bit of modeling of what it is actually going to take in order to get useful data on the Milky Way satellite population from Rubin. And so in this set of plots, I've binned things up by luminosity on the left and by distance on the right. And so in each bin, then there's the purple bar shows the total number of satellites in that bin. The light gray bar shows what you can straightforwardly observe with an 8 to 10 meter class telescope today. And then the gray bar shows what would be observable with the 30 meter class telescope. And so at the brighter magnitudes, -4, -5, and at the closer distances out to 100 kiloparsecs, we can get reasonable spectroscopy for these systems with the telescopes and instruments that we already have. But when you go down to fainter magnitudes, -1, -2, -3, and try to get out to the virial radius, then it's actually going to take 25, 30 meter class telescopes if we want to get spectra of everything. And if we don't do that, then it's going to be hard to make use of this population for physics and astrophysics. And so just to give a sense of the scale of what we're talking about, if you wanted to follow up everything that we expect Rubin to find, it would take on the order of 1 to 2 years of dedicated time with an 8 meter class telescope. I don't personally know of anybody with an 8 meter class telescope that is suggesting that they'll devote it to this. But if you do, then please let me know. All right, so next I'd like to go over some of the frontier areas where I think we're going to be pushing on the boundaries of what's currently known in the coming years, and examine where we may be able to get to. So one of these frontiers is the luminosity frontier, so pushing to even fainter systems. You might have thought that there would be a lower limit to the amount of stars that you could form in a dark matter halo. Like, let's say you always form at least 100 solar masses, solar luminosities of stars, or you form 0. This object, Unions 1, Ursa Major 3, was discovered 2 years ago with a total stellar mass of 16 solar masses. And so the existence of this thing suggests that, in fact, the luminosity function may go smoothly all the way down to 0. And maybe you can form 5 solar masses of stars in one of these satellites. Now, based on the data in the discovery paper, this object had a velocity dispersion of almost 4 kilometers per second, which translates to an enormous mass to light ratio, like 10,000. And that would make this the darkest known object in the universe. Will Cerny, a grad student at Yale, working with Marla Jiha, went back and re-observed all the stars with Deimos last year to check on this. And in Will's analysis, he identifies one of the brightest stars in the system as a binary star. which was inflating the velocity dispersion because the orbital velocity of the binary can easily exceed the velocity dispersion of the system. And then what he found with the higher signal to noise data is that the velocities of all the other stars also regressed significantly to the mean. And so with this new data set, we ruled out this initial dispersion of 4 kilometers per second and ended up with an upper limit on the dispersion of about 2 kilometers per second. So that suggests that there's no longer any evidence that this particular object is actually a dwarf galaxy. It's more likely to be the lowest mass cluster that's ever been found. We can't rule out that it has some dark matter in it, but there isn't any evidence in favor of that anymore. Now, what this object is emblematic of is that it has proven to be very difficult to determine firm classifications for most of the faintest systems, things with luminosities below about 1,000 solar luminosities. And so if you go back to our absolute magnitude half-light radius plot, almost everything in this lower left corner, we have not been able to measure a velocity dispersion or metallicity dispersion. And so another object that illustrates this is Bruce 2, where we have pretty good data on a sample of about 20 stars, but still we're only able to measure upper limits on the dispersion in velocity and the dispersion in metallicity. And so, based on our assumed definition of a dwarf galaxy, we're not able to draw any conclusions right now about what this object is based on the best data we've been able to obtain. So where does that leave us? I think there's a need to develop additional ways of trying to classify these systems. One possibility that's been explored in recent years by Sal Fu and Dan Weiss at Berkeley is to use narrowband imaging from HST to try to measure the metallicities of individual stars. The imaging uses a filter focused on the calcium K line, which, like the calcium triplet, is metallicity sensitive. And so by doing this, you get individual metallicities at the range of like 0.3 dex, so they're not as precise as the spectroscopic metallicities. But if you have a big enough sample, which you can get by going much fainter in the HST data, then you can still measure a dispersion. And so in this analysis, they were successful in measuring a dispersion for every system that they examined, even down to absolute magnitudes of -1 or so. So this is potentially one path forward, as long as we have something that gives us space quality photometry in the UV, which of course is not a guarantee going forward. Yes. Okay, so I would have to go back and check. It's probably either the stars with the smallest uncertainties are one of the histograms, and then the full sample is the other ones. But I would need to look. Another possible approach that's been explored recently is whether you can use dynamical mass segregation to separate dwarf galaxies from clusters. So if you have a system composed only of stars, then those stars interact with each other, and the heavier stars end up sinking to the center. The lower mass stars get puffed up. On the other hand, if the system is dynamically dominated by dark matter, that doesn't happen, and the radial distribution of the stars should be independent of their masses. And so that potentially gives us a way of indirectly determining whether a system has a dark matter halo, even if we can't measure how large that, or how massive that halo is, but by measuring the relative spatial distributions of the more massive and less massive stars, we can hope to determine whether some of these objects are galaxies or not. There is a caveat to that, which is that if the mass to light ratios, if the dark matter content is lower than in a typical ultra-faint dwarf, then you can, then the relaxation time can get short enough that you do actually still end up with some mass segregation, even in a system that is formally dark matter dominated. So we do need to be careful about how we apply this. A related frontier that we are trying to push on is the low velocity dispersion frontier. This is related because there's a correlation between the velocity dispersions of dwarf galaxies and their luminosities, such that at the faint end, we end up just measuring upper limits for many of the systems. And so, as I mentioned, the smallest velocity dispersions that we've been able to measure for these satellite galaxies and clusters is about 2 kilometers per second. So what does it take to actually be able to measure a velocity dispersion less than 2 kilometers per second? So you can make a little toy model, assuming different velocity dispersions, assuming different sample sizes for typical measurement uncertainties per star. And at the level of 3 to 4 kilometers per second, even with a pretty small stellar sample, it is straightforward to measure a velocity dispersion. When you get down to an assumed intrinsic dispersion of 1.5 kilometers per second, then even with 20 to 30 stars, your chances of being able to robustly measure the dispersion are not that good. And so what this is pointing to is that we need to be able to measure the velocities of individual stars more precisely. Now, most of the data that we have right now are from medium resolution slit spectrographs at R of 6 to 10,000. And those are really limited to velocity precision of about 1 kilometer per second. There's not an obvious path to improve that further. Fiber spectrographs, such as BLT on flames, do enable you to do better. And so my student, Sasha Mintz, is working on seeing how well we can do with those data. And then we're also building a new spectrograph at Carnegie in collaboration with Harvard called the VIA spectrograph. There's actually going to be 2 of these. One will go on the Magellan telescope and one will go on MMT. So we'll have dual hemisphere coverage. The instrument will have 600 fibers and a 1 square degree field of view. And the target velocity precision is 100 meters per second. So that, in principle, will enable us to push down by an order of magnitude relative to current data. And we hope that that will be a significant contributor to being able to characterize these very faint satellites. All right, so another frontier that we are exploring is the binary frontier. So from very early on, people have raised the concern for these faintest dwarf galaxies that when we measure a velocity dispersion, it might be biased because of binary stars. So a binary can have an orbital velocity of 10 kilometers per second, 20 kilometers per second. And so it doesn't take very many of those to bias your intrinsic velocity dispersion of 2 kilometers per second or 4 kilometers per second. And then what has more recently made this particularly concerning is results from Max Moen collaborators showing that the binary fraction, the close binary fraction of stars goes up as you move to lower metallicity. And so whereas at solar metallicity, maybe 20% of your stars are in close binaries, at F(h) of -2, where the dwarf galaxies are, it's more like 50% of those stars are in close binaries. So what do we know about binary stars and dwarf galaxies? Essentially nothing up until very recently. In the literature, there are a total of 2 binary stars and dwarfs that somebody has at least claimed to measure an orbit for. Those are shown here. There's one object in Hercules with a period of a few months and an amplitude of 14 kilometers per second. This second object, there aren't actually even enough data to resolve this period alias. And so we don't officially know the properties of this binary, although you can say that the amplitude is relatively large. And that's it in terms of orbits. So there are other ways that you can try to constrain the binary fraction. One of which is just to analyze the color magnitude diagram, which was first done by Marla Jiha in 2013. So she did joint fitting of the initial mass function and the binary fraction in HST observations of some of these dwarfs. And although in the best cases, like for Hercules as shown in green here, you do get reasonable constraints on the binary fraction, that it's between 30 and 60%. In fact, if you look at the 2 sigma uncertainties, then the binary fraction can more or less be anything in these systems. Another approach is to use HST or JWST data just to directly identify the binaries. And so we first explored this a couple of years ago with Mohammad Safarzadeh in HST data, and then Cheyenne has done a very nice analysis of a couple of dwarfs last year with much more sophisticated methodology. So here are examples of what some of these binaries look like. We're sensitive, given the resolution of HST or JWST, to separations above a few thousand AU. And then if you look at the number of pairs as a function of separation, you see this excess from 3,000 up to 10 or 12,000 AU that demonstrates that these are genuine wide binaries in the dwarf galaxy rather than just chance superposition of stars. And so in the 2 galaxies that this has been looked at, the wide binary fractions are on the order of 1%, which is similar to what's seen in the solar neighborhood. And then if you make a wild extrapolation of that to what the overall binary fraction is, then you'd find something on the order of 50%. You can also do things where you, let's say you observe a set of stars in dwarf galaxy multiple times, not enough to map out their orbits, but enough to see if the velocity of any given star is potentially changing. And so Quinn Miner did this for Reticulum-2 several years ago and found a preferred binary fraction of basically 100%. But nevertheless, concluded that the velocity dispersion of the system is only overestimated by about 20% if you correct for those binary motions. So even though the binary fraction is very high, it doesn't seem to be biasing the dark matter inference too much. And so this lack of robust information on the binaries in these galaxies inspired me a few years ago to start a project actually trying to identify and measure the orbits of these systems. This project I worked on with one of your recently graduated undergrads, Damani Sharkey. So this started as a surf project. And what it has turned into is a magnitude limited survey of the brightest stars in every ultra-faint dwarf that we could observe from Magellan. And so those stars are shown in the color magnitude diagrams here. We took everything brighter than 17th magnitude. And most of these stars were originally identified and confirmed as dwarf galaxy members with spectra between 10 and 20 years ago. So that actually gives us now a pretty good time baseline that we can use to search for radial velocity changes. And so from this sample, we find that about a quarter of the stars show clear radial velocity changes on timescales of 5 to 10 years. If you take the distribution of orbital periods from the Milky Way in the solar neighborhood, we would be sensitive to about 25% of the binaries. And so that, very roughly suggests that indeed we may be in a situation here where the binary fraction is close to, if not exactly equal to 100%. And so certainly this motivates more work from the dark matter perspective to confirm that this is not biasing our inferred masses. We've now, for the first time, been able to determine orbits for at least a small set of stars. We find orbital periods ranging from a few months up to 10 years, even close to 20 years in some cases. Most of these binaries have quite small amplitudes, but there are a few with more massive companions that we've identified. And we'll have a few more of these that we can complete the orbits for soon. Now, so what does it mean if the binary fraction is 100%? So you can do a toy model where you say the intrinsic velocity dispersion of some set of stars is 0. And so the only dispersion that you measure is a result of the binarity of these stars. And for a sample of the typical size that we have in dwarf galaxies with typical velocity uncertainties, here's what you get. So for a population that's 100% binaries where you measure each star once, then there's about a 50% chance that you will, just from the binary orbital motions, measure a dispersion that's above 2 kilometers per second, which is getting into the range that we actually observe for many of these systems. However, fortunately, you can avoid this relatively easily. If you just get a single second epoch a year after the original measurement, then you find that, and use that to discard the obvious binaries, then you find that only 14% of the time do you get a significant velocity dispersion for a population that has an intrinsically 0 dispersion. And so this has, in fact, basically been the approach that we've mostly taken in these papers for the last decade. And so what it means is that anytime you see a velocity dispersion measured from single epoch data, you should take it with a very large grain of salt. But as long as measurements are made multiple times for at least a significant fraction of the stars, then there shouldn't be a significant concern that you are inferring a significant dark matter mass for a system that, in fact, does not have any dark matter. And so then the other frontier that I'd like to go over is this, the small size frontier. So as I mentioned, these objects in the lower left corner of this plot have proven very difficult to classify. In fact, very few of these objects at the smallest sizes have been observed at all until now. So some of them have been known for many years and were classified as globular clusters. One example is Palomar 13. And more than 20 years ago, Pat Cote, when he was a postdoc here, measured a velocity dispersion for this system and found that it suggested that the mass to light ratio was about 40, which would imply a dark matter content, and this thing was not actually a globular cluster. So in collaboration with George, while I was here as a postdoc, we went back and got multi-epoch demo spectroscopy, and indeed concluded that, as suggested by the previous section, this is from binaries. And when you correct for the binaries, then we're only able to measure an upper limit of about a kilometer per second for Palomar 13. So based on this, I concluded that these objects were not interesting, and essentially nobody observed them for the next 10 years because of that. Some of my collaborators proved a little bit more insightful and decided that they were worth pursuing anyway. And so what this has resulted in is a spectroscopic campaign with IMAX on Magellan and Deimos on Keck, covering 19 of these compact satellites that we're terming ultra-faint compact stellar systems. This is led by Will Cerny at Yale and Ting Li at Toronto. And so for each of these objects, we're able to identify member stars, measure their spatial positions, color magnitude diagram, the velocities, proper motions from Gaia, as well as metallicity. When we put these measurements together, we find that these compact systems are, not surprisingly, kinematically cold. In almost every case, we just get an upper limit on the dispersion. There are two objects where we do actually measure a non-zero dispersion of 2 or 3 kilometers per second. Both of these have single epoch data only, and so we are not claiming anything about the dark matter content based on the data that we have right now, but we are hoping to get a second epoch and make sure that this is not just due to binaries. The metallicities of these systems are a bit more interesting. So they span almost a factor of 1,000 in mean metallicity, going from above -1 for the most metal rich down to close to -3.5, well below any globular clusters that have been identified. And so in this plot, these objects are compared to the dwarf galaxy population, which is shown in blue with the luminosity metallicity relationship, and with the globular cluster population, which is shown as the gray X's. Globular clusters show no relationship between their stellar mass and their metallicity. And so, and they do go up to quite high metallicities in some cases. So it seems clear that the most metal rich of these ultra-faint compact systems are clusters, but there's also a group of potentially up to half of them that are in the dwarf galaxy regime in this plot. So this is at least suggestive that some of these could in fact be dwarfs that were discovered 10 or 20 years ago and just weren't recognized as actually being dwarf galaxies. So we've also investigated a couple of these in more detail, specifically Delve-1 and Eridanus-3. And what's unique about these two systems is that they each have one star that is several magnitudes brighter than the next brightest star. For Delve-1, the brightest star is about 16th magnitude, so that's quite easy to get a high resolution spectrum of. For Eridanus-3, the brightest star is like 19.5, which you can very painfully get a high resolution spectrum of with Magellan or Keck. And so we've done that, measured the chemical abundance patterns, and found some pretty surprising results. So in both cases, the metallicity of the brightest star is extremely low, around -3, below that of any of the Milky Way globular clusters. These stars are both extremely strongly carbon enhanced. You can see the saturated carbon absorption in the G band here. So they're carbon enhanced by almost a factor of 100. And critically, neither of them shows an excess in neutron capture elements. So these are stars that belong to a class that's known as CEMP no stars. They're carbon-enhanced metal poor stars without an enhancement in S-process or R-process elements. No such star has ever been found in a globular cluster, as far as I know, but they're common in dwarf galaxies. And so the chemical abundances of these two systems suggest that they're more consistent with being dwarf galaxies than with being clusters. So that leaves us with two scenarios to consider here. So either these things are dwarfs, which would tell us that dwarf galaxies can actually extend to much smaller sizes than has previously been recognized, and the population could be 30% larger than we were aware of. And so if that's the case, then spectroscopy of additional stars in these systems should show stars with a range of metallicities and a range of abundance patterns. Alternatively, if these things are actually clusters, then we should find, by observing additional stars, we should find that all of them have the same very low metallicity and large carbon enhancement. And so that is a very different abundance pattern, as I mentioned, than is seen in globular clusters. And so that would suggest that these are clusters that underwent a different formation history and chemical evolution pathway than classical globular clusters. Maybe it's telling us that the very first clusters that formed are carbon rich. This could align with what we're seeing with JWST spectroscopy of some of the highest redshift galaxies, which also show large carbon abundances. And so I think either of these possibilities would be quite interesting. So we are in the process of obtaining spectra of the next brightest stars in each of these objects. I'm not prepared to make strong claims, but we do see tentative evidence for variations in both metallicity from star to star and the carbon abundance, which would favor the dwarf galaxy hypothesis for these objects. And so please stay tuned for a more comprehensive analysis of these data. All right, so the final frontier is the distance frontier. I will skip over this in the interest of time, but obviously Rubin will enable us to discover these faint galaxies outside the virial radius of the Milky Way for the first time. And importantly, it will enable us to find some objects that are actually isolated and so have evolved without tidal influences and without influence from reionization of larger galaxies nearby. So what we are hoping to do with spectroscopy of the satellite galaxies in the coming years is to characterize the full satellite population, try to confirm what the connection is between the known ultra-faint dwarf galaxies and these more compact satellites that we are now studying more recently. We should be able to gain more insight into the faint end of the luminosity metallicity relationship, where things may hit a plateau and certainly are not in very good agreement with numerical simulations. And we might be able to study the properties of isolated ultra-faint dwarfs for the first time. So just to quickly summarize, I think one conclusion that I've come to is that it's already a challenge to get useful spectroscopy of the faintest stellar systems, and that's going to cause us a lot of problems in the Rubin era when there's even more that we want to follow up. And so this motivates the development of more efficient spectrographs and hopefully a lot of telescope time, but of course we need to make the case that that will be useful. We're finding evidence that the binary fraction in the faintest dwarf seems to be quite high, possibly up to 100%, and so you really can't learn anything about them unless you get multi-epoch velocity data to exclude those binaries. And even with that, I think it's going to be a challenge to understand the faintest satellites without exploring kind of new methods for classifying them and separating dark matter dominated systems from the star clusters. Thank you.
Questions for Josh? George?
So, I think you can do that empirically. Let me get back to one of these half-light radius and absolute magnitude plots. So, yeah, I think the sizes of these things are more consistent, and the surface densities are more consistent with the globular cluster population for sure, and that is partly what led me to dismiss them as clusters for many years. But I think there's not, we don't have a good physical reason to believe that that's actually telling us the true nature of these systems. Yeah, so I mean, I think that, yes, that as as I argued with, basically with this plot, where we see some of them are very metal poor, which are not aligned with the globular cluster population. So I think the challenge here is that all of these are empirically motivated classifiers and not physically motivated ones. And so they certainly point us in one direction, but I'd be more comfortable if we had an understanding of why that is the case, and we see different properties for the clusters and the dwarfs than just assuming that that's how it works.
Agree?
Yeah, so in the data that we have so far, there's no excess seen beyond about 12,000 AU, which is still a small fraction of a parsec. However, the sample of such binaries is very small, like we're talking about a couple dozen of them. And so if the separation distribution is such that it's less probable to find things that farther out, then you would need a much bigger sample for that actually to give you a constraint. There have also been papers suggesting that you can use this to constrain the degree of dark matter substructure within one of these dwarfs, because that will disrupt the wider binaries. But again, I think you need significantly better statistics than we have right now in order for that to be a useful constraint. I don't think so. So the stars that we have metallicities for are almost exclusively the red giants. And so the luminosities of, even if the companion star is the brightest it could be, let's say it's at the main sequence turnoff, then the fraction of light coming from the secondary is going to be pretty small. And then the other factor is that the calcium triplet lines from main sequence stars are much weaker than for giants. And so I think that would be a very small bias to the equivalent width of the calcium triplet.
Costa?
Does what affect that distribution? So Kareem is the expert on this. I think there's not very much evidence that the wide binary fraction is metallicity dependent. And I think that is consistent with what we know about how binary stars form. But I don't know that we have a strong enough understanding of that you would say that it's definitive.
Yeah, great. We should wrap up, but we'll continue questions outside at Wine and Cheese. So thanks again, Josh.